One unique feature to aldehydes and ketones is that they're both relatively electrophilic. So let's compare the two. And so we'll just compare aldehydes versus ketones. And we'll try to predict, all right, if they're both electrophilic, which one's more electrophilic? Okay, so let's just draw out a generic aldehyde right here. And as you can imagine, we have a resonance structure where we can pull electron density up and out of that pi bond. And if we do that, we have an oxygen with a negative charge, and we've got a carbon with a positive charge. So we've got a resonance structure for an aldehyde down here. Makes sense? And now let's compare that to our ketone. It's going to look remarkably similar, where again we can pull these pi bonded electrons up and onto this oxygen, giving the oxygen a negative charge and the carbon a positive charge, and this would be our ketone resonance structures. We know the resonance structures on the right for both of them are going to be minor contributors because they don't have full octets, but they're still valid resonance structures. All right, so the question is, which one is more stable and which one's less stable? Well, really, when we're looking at this, what we can focus in on is this carbocation, right? Really, that's the main difference here. So if we think about the stability of the carbocation in the resonance structure on the right, we can say, well, this one is going to be more substituted, which means it's going to be more stable. Okay, conversely, that means that this is less stable because it's less substituted, and that means that it is going to be more reactive. So typically, aldehydes are going to be better electrophiles than ketones because that carbon in the CO double bond is going to be less stable and therefore more reactive. So let's make a note of this. So note is that aldehydes are typically more reactive. This isn't true 100% of the time. In organic chemistry, there are a million exceptions, and there are exceptions where some ketones are more reactive than aldehydes, but this is generally true. So it's something we should remember. All right, so if the highlighted carbons are electrophilic, that means we could have some sort of nucleophile attack into them, creating an intermediate. So let's take a look at a simple mechanism where a nucleophile can attack one of those carbons. And we're going to start off with a simple basic mechanism. And I'm just going to write under basic conditions, meaning not acidic. All right, and this is going to be pretty straightforward. And I'm going to stick with an aldehyde because we know it's more reactive, but you can do the same mechanism with a ketone. And like we saw, there's a resonance structure where you can show this where the oxygen has a negative charge and the carbon has a positive charge. You don't have to show these resonance structures, but I'm going to show it in this example. And then you can have some sort of nucleophile. In this case, I'm going to have it be negatively charged because it's under basic conditions. And this nucleophile can attack into this carbon. Right? It doesn't matter which resonance structure you use. If we were to use the other resonance structure, you could show it, but you need to have two separate arrows. So it doesn't really matter. Just pick one. Okay, so we've had it attack in. This is under equilibrium conditions. So what we'll get is a new nucleophile carbon bond, and we'll get this tetrahedral intermediate. And then in the second step, what we're going to do is we're going to quench with some sort of acid in order to get our neutral product. So there we go. We've got our nucleophile adding in under basic conditions. All right, I did want to make an important note here, and that is under basic conditions, you want to avoid any organic intermediate with a positive charge. So if you go through and you look at all of these, this has no net positive charge, this has no net positive charge, no net positive charge, and no net positive charge. It is okay to have other reagents with a positive charge, but our main organic reagents, you don't want to have a net positive charge. All right, so that's an important trick whenever you're doing organic mechanisms. Let's take a look at this mechanism under acidic conditions. This time it's going to be a little bit different. And again, I'm going to start with my aldehyde. And we know that we're going to have acid around because I just said it's under acidic conditions. So I'll show that as just H+. And this is under equilibrium, so I'll show equilibrium arrows. And then our nucleophile in this case isn't likely to be negative because if it were negative, it would likely just get protonated by the acid. So the nucleophile is probably going to be neutral and it's going to have some sort of proton coming off of it. All right, in the first step, we've got acid, so we could protonate that carbonyl compound. So in this case, we're using an aldehyde, so we could protonate that CO double bond in our aldehyde and get this intermediate right here. All right, in the next step, we still have that nucleophile. And the nucleophile now can just attack that same electrophilic carbon. In this case, it's actually more electrophilic because the oxygen's now got a positive charge, and kick electrons up to that oxygen. And now we've got our alcohol. We've got our nucleophile with a positive charge on it because it's now formed a new bond. And then in that last step, I can just write minus H+ to show a deprotonation event happening. And we can get rid of this proton right here during that last step. All right, so if we go and compare the two, right? Under the basic conditions, you can see that the protonation step happened last, where in the acidic conditions, it happened first. So that's one main difference. The other difference is our nucleophile under the basic conditions normally has a negative charge, and under acidic conditions, it's normally a neutral compound. So really there's subtle variations, but in either case, it gives you this exact same product. So it is important to know which mechanism you should draw whenever you're doing this on paper. All right, just like we made the note up above about basic conditions, I wanted to do one down here for acidic conditions. So under acidic conditions, the opposite is true. So avoid organic intermediates with a negative charge. So if we look at this, there's no negative charge there. If we look at our nucleophile, no negative charge there. If we look at this one, no negative charge there. If we look at this one, no negative charge there. And then our final product, no negative charge. So try to always pay attention to whether or not you're running a reaction under acidic or basic conditions. All right, so let's make some notes. And these notes are important for both acidic and basic reactions. And the first one is that the reaction is often at equilibrium especially if your nucleophile is in decent leaving group. And let's take a look at why that might be the case, right? So let's take a look at the acidic conditions. So what I mean is let's focus in on this and figure out how it might be reversible, right? So in this step, actually let's focus in on this. In this step, if our nucleophile is a good leaving group, we could just kick it right back off and go in the reverse direction. So really it depends on how easy it is to kick off the nucleophile during one of these intermediate steps. So the reaction is at equilibrium if that reverse reaction is somewhat plausible. All right, so then the question is, how can we favor our product? There's a few different ways. So let's list both of those. The first one is the product can be favored if your nucleophile is a bad leaving group. So that's one way we could just push it completely to one direction, meaning the product side. The other one is just by forcing it, right? So you could use a high nucleophile concentration. Basically meaning just flood the reaction with so much nucleophile that you're going to push the equilibrium to the opposite side using Le Chatelier's principle. All right, and then the last note is that the aldehyde tend to favor nucleophilic addition more. More than ketones. So that's important to keep in mind too. All right, so to finish up, I wanted to talk about what nucleophiles we could use. So let's come up with a common set of nucleophiles that could be used under the acidic or basic conditions. And I'm going to set these up into three groups. I'll have oxygen-based nucleophiles right here, and we'll make a list. All right, so for oxygen, the easiest and cheapest nucleophile is water, followed closely by some sort of alcohol. It could be ethanol, methanol, something like that. It doesn't really matter. Conversely, if we wanted basic conditions, we could just use hydroxide, or we could use an alkoxide, right? So the difference between these are whether or not it's acidic or basic. The other one that we'll look at in our next set of videos is kind of different. This is ethylene glycol. This is actually used to protect ketones and aldehydes by making what's called a cyclic acetal. We'll look at this mechanism in more detail later, but really both of these alcohols can act as nucleophiles, which is kind of unique. All right, so oxygen nucleophiles are listed. Let's do sulfur next. Sulfur, we could have something similar with H2S. We could have some sort of thiol. We could have some sort of analog to all of our alcohols and just list them. Really, sulfur is a lot like oxygen, but in this case, it's actually even more nucleophilic. So this makes a really great nucleophile. All right, let's do nitrogen next. And with nitrogen, you can have amines. So really any sort of amine. However, you don't want your amines to be too hindered. So really, you only go up to secondary amines. Normally you don't do tertiary amines. Tertiary amines are simply too bulky to make very good nucleophiles. So I'll draw this, and then I'll write an X through it, and then I'll say too bulky. All right, And then students will ask, what about nitrogen with a negative charge, right? We've got oxygen with a negative charge and sulfur with a negative charge. What about nitrogen with a negative charge? The problem with nitrogen with a negative charge, let's even write it down, is that this is way too basic. It'll do acid-base chemistry. So it's typically not used as a very good nucleophile because it'll just do acid-base chemistry before that nucleophile has a chance to find an electrophile. All right, next one is hydrogen nucleophiles. All right, and these are pretty easy. If you think about hydrogen acting as a nucleophile, it must be H-, right? So not a proton, but H-. And we've seen this used in NaBH4, that's a hydride source, and LiAlH4, lithium aluminum hydride. Both of those are good sources of H-, meaning sources of hydride. So good nucleophiles. All right, last but not least, we've got carbon. And with carbon nucleophiles, we need a carbon with a negative charge. We've seen that with Grignard reagents. So I'll just abbreviate that RMGX, where X could be any halogen, but that's our code for a Grignard reagent. You could have something like cyanide, where that carbon with the negative charge actually makes a pretty decent nucleophile. You can also have acetylides, which is just a deprotonated alkyne. That carbon at the end of a deprotonated alkyne has a negative charge, therefore it's a pretty good nucleophile. And then the last one we're going to look at, we'll cover this reaction later, but it's kind of unique. It's got phosphorus bonded to carbon. And the phosphorus has 4 phenyl groups. And if you remember, phenyl groups are just rings that look like this. So this whole ring right here is going to be a phenyl group, but I'm just going to abbreviate that for simplicity's sake. And then the carbon still needs to have a negative charge, so we'll draw that in like that. And this could have any sort of hydrogens or R groups coming off of it. I'll just keep it as 2 hydrogens right now. This is called a Wittig reagent, and so we'll look at that reaction a little bit later. All right, so that's where we'll stop today. Before we get too much further, though, I did want to give you a hint on pod 5 since it's a little bit tricky. In pod 5, it says that this is glucose. What I've done is I've redrawn it over here in a easier to view form. And you can see right here, we've got an aldehyde, right? And you can see we're dealing with acidic conditions. And then the new bond that we're forming is right here or right there. So it looks to me like this oxygen for this alcohol is adding into that aldehyde and forming a new bond. So what I want you to do is I want you to draw a complete stepwise mechanism for this reaction. And if you want, just start with this type of drawing as your starting material rather than this. It makes it a lot easier to draw all of your intermediates. All right, good luck studying and let me know if you have any questions.